Now here we will discuss the eigenvectors and the eigenvalue. So as a start, let us differentiate what is eigenvector and what is eigenvalue. For the eigenvector, it is also called as the characteristics vector. So it should be a non-zero vector and it changes by a scalar factor obviously with the linear transformation application. Whereas the corresponding eigenvalue, which is denoted as lambda, so this is the symbol for the eigenvalue, this is the factor by which the eigenvector is scaled. And for this eigenvalues, these are a spatial set of scalars that associated with linear system of equations. And these eigenvalues are also known as the characteristic roots or characteristic values. And for the main concept of the eigenvalues and eigenvector, so we have it here that the statement that the product of any matrix A with the eigenvector is equal to the product of the eigenvalue and the eigenvector. And then from here we can have, or we can derive an equation that we can use in dealing with eigenvalue and eigenvector topic. So from here, as we discussed a while ago, that the product of any matrix A with the eigenvector is equal to the product of the eigenvalue lambda and the eigenvector. Now here the given matrix here should be a square matrix, means the number of columns and number of rows are equal, and the eigenvector here should be a non-zero vector, and the lambda, which is the eigenvalue, is the scalar. Now from here we can now derive the equation or principle that we can use. So from there, since the product of the matrix and the eigenvector is equal to the product of the eigenvalue and eigenvector, so from here, algebraically, we can simplify this statement by transposing the product of the eigenvalue and the eigenvector. So it becomes minus, and then obviously we can have a factor of eigenvector. So we will have it here that in order to factor the eigenvalue, so we have to multiply by the identity matrix. Anyway, this is only an identity matrix. Now basically we have that any value that multiplied by 1 is equal to the number itself. So when it comes to matrix, this is just simply similar to that concept. And then we can factor out the vector. So the other factor will be matrix minus the product of the lambda or eigenvalue times the identity matrix. And this is, we call this as our equation now, which is also known as the characteristic equation. So then, if we will consider the eigenvector is a non-zero, therefore we have a solution that this is now the determinant of A, matrix A, minus the product of the eigenvalue, and the identity matrix is equal to 0. So we can use this equation in dealing with eigenvalue and eigenvector problem. So we call this as the characteristic equation, where obviously the lambda here is the eigenvalue, the A is matrix, and identity matrix for the I. Now for the given example here, we have to look for the eigenvalues. Now the given matrix is a 2 by 2 matrix whose elements are -6, 4, 3, and 5. Now we will use the equation or characteristic equation here. So we have it here as the matrix A. So the elements are -6, 3, 4, and 5. And then we have negative or minus lambda multiplied by the identity matrix. Now we all know that identity matrix is a square matrix whose elements in the main principal diagonal are 1 and then off are 0. And then, since eigenvalue, the lambda, is a scalar, so we can multiply the scalar to each element of the identity matrix. So we have here as lambda times 1, lambda, lambda times 0, 0, 0, lambda times 0, 0, lambda times 1, lambda. And then we can subtract the two matrices since they have the same order. So we can subtract as negative 6 minus lambda. So negative 6 minus lambda. 3 minus 0, so that will be 0. 3. 4 minus 0, so 4. 5 minus lambda, 5 minus lambda. So we have it here as 2 by 2 determinants. Then we can evaluate the determinants. So just simply get the product of the principal diagonally downward minus the principal diagonally upward. So negative 6 minus lambda times 5 minus lambda minus 4 times 3, that will be 12. Then we can multiply this product of two binomials by just simply applying the FOIL method. FOIL means first, outer, inner, and last. So first term, negative 6 times 5, that will be negative 30. And then the outer, negative 6, negative lambda is positive 6 lambda. Inner, negative lambda times 5 is negative 5 lambda. And then last, negative lambda times negative lambda is positive lambda square, and then minus 12. Then combine similar terms, we have lambda square, 6 lambda minus 5 lambda is positive lambda, then negative 30, negative 12, negative 42. So we have it here a quadratic equation. Then we can factor this quadratic equation by means of trial and error. So we have to look for the factor of lambda square, lambda times lambda. And then the factor of 42, negative 6 and 7. So this will be our factor for that equation. But before you will get the roots, just check first if this factored form is correct by just simply applying the FOIL method again. Multiply the first, lambda times lambda, and that is lambda square. Outer, 7 lambda. Inner, negative 6 lambda. So positive lambda minus 6 lambda is positive lambda. And then the last, negative 6 times 7 is negative 42. So it means to say that this factored form is correct for this quadratic equation. Then all you have to do next is just equate each factor to 0. So lambda minus 6 equal to 0. Lambda plus 7 equal to 0. So we have the value of lambda as transpose the 6. It becomes positive 6 transpose the 7, negative 7. So these are the eigenvalues. One is 6, the other one is negative 7. Another example here is that matrix A has elements 0, negative 2, 1, and negative 3. So similarly, finding the eigenvalues or the roots, we will use this characteristic equation. So we have the matrix A. So input or enter the elements of the matrix A. 0, negative 2, 1, negative 3, and then minus lambda to be multiplied by the identity matrix. Then we have to multiply the lambda by the elements of the identity matrix. So we have lambda times 1, lambda, lambda times 0, 0, lambda times 0, 0 again, lambda times 1, and that is lambda. Then we can subtract these two matrices. So 0 minus lambda, negative lambda, 1 minus 0, 1, negative 2 minus 0, negative 2, negative 3 minus lambda, negative 3 minus lambda. Next step, evaluate the determinants. So this is also a 2 by 2 determinant. Multiply the principal diagonally downward, negative lambda times negative 3 minus lambda. So negative lambda times negative 3, positive 3 lambda. Negative lambda times negative lambda, lambda square, positive. And then minus the principal diagonally upward, negative 2 minus negative 2, so that will be positive 2. So negative 2 or minus 2 minus negative 2 is positive 2. Again, we have a quadratic equation here. So we can factor by trial and error again. So factor of lambda square, lambda, and lambda. Factor of 2, 2, and 1. And then before we will extract the roots, we have to check first if the factored form is correct. So lambda times lambda, lambda square. Outer, lambda times 1, lambda. Inner, lambda times 2, 2 lambda. So 2 lambda plus lambda is 3 lambda. Last, 2 times 1, 2. Then, this factored form is correct for this equation. The next thing to do is you can extract the roots, equate each factor to 0, and then transpose the 2, it becomes negative 2. Lambda plus 1 equal to 0, so lambda is equal to negative 1. So these are the eigenvalues or the roots of this quadratic equation.